All right, welcome back everyone to the seminar series on fractional calculus. Today, it's my great pleasure to introduce Professor Oleg Marichev. Oleg Igorovich Marichev is a Soviet and American mathematician. He graduated from the University of Belarus, where he continued his studies to earn a PhD. His scientific supervisor was Fyodor Gakhov. He is the author of more than 10 books on integrals, integral equations, fractional calculus, and special functions, including the famous textbook, together with Stefan Samko and Anatoly Kilbas, on fractional integrals and derivatives, theory and applications. Around 1990, he received the DSc degree, or habilitation, in mathematics from the University of Jena, Germany. In 1991, he began to work with Stephen Wolfram on developing the Mathematica system, where he implemented Mayo-G and other functions and operations using original algorithms. He is the developer of the Wolfram functions site with more than 307,000 formulae, which can be found at functions.wolfram.com. And today, it is our great pleasure to hear from him a presentation about integral transforms with Fox H functions in kernels. Please, you can go ahead.
Dear friends, dear colleagues, I am happy to start to talk about my activity in special functions and integrations. I'm working in Wolfram research by invitation 35 almost years. And the main aim for me was to implement algorithm for evaluation integrals, which in reality based on theory Meyer and Fox H functions. And this algorithm is so powerful that practically 80 maybe percentage of all integrals which you can meet somewhere published in literature, in handbooks, are the cases or very close related to this algorithm. Let me start from Fox function. What is it? Here you see definition of Fox function. Basically, it is integral by special contour. Contour I will show below a little. From ratio of products of Meyer of gamma functions. And we see here 4 groups gamma functions. One group, other, and one more. Gamma function has poles and residues of this in these poles produce output after evaluation integrals of such type. This integral is called Mellin-Barnes integral. Mellin-Barnes. Because they appeared, in the beginning of last century, and even before, in 1888, Pincherli, if I remember correctly. No, so horrible big expression is very difficult to understand and accept for beginners. And I show you how very known exponential function can be represented through this value. Let me evaluate again. In Mathematica, I use two commands comment which we together with Paco Jane develop. It is Fox H form and also Meyer G form. And you see that we get Fox with only two components. So instead large products, we will get only one gamma function here. And in this case, I used a different comment in kernel. It's also basically my code, but old code, not so powerful for Meyer G function. And then it was extended for Fox reduce, more generic case. It was done by Tigran Ishkhanyan. I am showing now beginning of our article about these functions. And here you see Mellin transform, definition Mellin transform. And if you look accurately, Mellin transform of Fox function, Fox function, it is, I defined it up, produce gamma product, which you saw already. But here I put index L equal 1, 2, 3, and corresponding L added to each of these components, coefficients. Fox has a lot of particular cases. Below you will see these cases in my lecture. And the most important case when coefficients before S is 1. And here we see this 1, 1, 1. And we see that this function is particular case from Fox. I did not write formula. Maybe I should write formula for this situation. Also, I forgot to say in previous, oh, yes, 111 here should be. I forgot to remove 1, 1 on position second coefficient. And this is component from my previous notation for Fox function. Here you can see interactive plot which was done by my colleague Marco. Let me evaluate this. I can change something. No, for example, right here 2 pi. And here you see that function actually is z plus 1 in power, such power, multiply on this, represented it through gamma function. You see only two gamma function. And it is case of Meyer G function, of this Meyer G function. This is more complicated contour. I will write here, for example, 3. And again, you see contour started from this point and goes to top, and all left poles should be in left side, poles, red poles should be in right side. And here we cannot make direct straight line, vertical line like we made in previous situation. So it is different situation. And this is more complicated again. Situation can evaluate. You see the function representable through gamma functions. You see how contour goes when we have sets of poles and so on. No, it's enough for presentation to these two functions. These two functions, Fox and Meyer, collect a lot of very different by quality particular cases like logarithm, exponential function, and others. But here we wrote sentence which shows how integrals from Fox function or product of this Fox function can be described using convolution property or Parseval relation for Mellin integral transforms. These relations I show above. Here I present a result of relation of three integral from three function. This is one Fox function, other, and one more. And this integral, it is like, for example, integral Mellin transform from this product functions. Or it is sinus Fourier transform from product of these two functions. Or Hankel transform generalized a little from this product functions. So in one integral we accumulate so many, and I am sure that people never saw such constructions, such type constructions, because you see here rather big expression in degree K1, in degree K2. It is a series with very complicated structure, double summation, no name for such generic functions, and this product, this unit step regulate existence this term in summation. So basically we have three double sums, and from these three double sums one always exist in result, but other can appear or not appear, because unit step can be 0 or 1, and automatically regulation provided by this one. Below you see more simple case for G 1, 2, 3, 1, 1, 3, 2. And again, it is more clear maybe to understand situation with a unit step here. I verified these results, but in how much years? In 1978, in my book, I made mistake, and now at last I fixed this mistake in description this integral. My first book was translated on English, and in reference you will find it. Also, you can find in Wikipedia information about me. Here we have reference. I collected this reference for the following purposes. I hope to make super handbook, which include practically all published in literature integrals. As I mentioned, a lot belongs to this algorithm for evaluation. Now, I continue. Here I give example integral transforms. Integral transforms and much more. You can find this if you go to resource function generic integral transform. You can load this and you can get this list. Now it is something like 15 maybe or less integral transforms. No, here Hankel, you see. Below I show how it works. And all these transforms are cases of so-called H transform. H transform here. It is it includes Fox function in kernel. I will show how it works below. No, here some kind games we can generate. No, let me show. We can generate this guy. Already generated. I should take this guy. I will try to show a little. Randomly, we can generate function. And then from this function, we can make either Meyer form or we can evaluate transform. Here I show Hankel transform, and in previous my experiment was logarithm. You can play with this game. Here I show example verification. Again, I verified concrete random functions and result coincide. Or I'm sorry that I put this one. It's mathematical feature. It's my mistake. But you can repeat my evaluation and fix this, remove these numbers. Yeah. Now we can start to talk about test. No, test here only 186 functions, and you see all these functions. We can load this test, and then we can run. What can run? We can run Meyer Fox H form from each of these functions. I will not do this, but it works very fast. You see so many seconds we need for evaluation. One I will fix. And this table, for example, absolute value produce such Fox representation. You can do it yourself after my lecture, and you can then verify table form. And at last, here, only now I mention mistake. I should not use that formal. By this reason, my output includes this Z. I will fix this mistake. Put Z and evaluate without mistake. No message, it's usual. Meyer does not like table inside. Code for Meyer I wrote together with help Jerry Kuiper. It was happened at last century and 30 years ago. And I put message which should be removed somehow. No, in any case, you see situation here. Oh, only two. Is not working two cases. All other work. And then we can do this for inverse Laplace transform. Again, mistake. Z should be here. We can evaluate. You see, about 2 seconds, 146 examples. It is inverse Laplace transform from which function? No, from this function, for example. About conditions of convergence, I omit right now here this question. But if you remember, I am course and I can say main developer of 5 volumes, right now 6 volumes, integrals and series, together with Prudnikov and Brychkov. And volume 5 devoted inverse Laplace transform. You can find there many information, very interesting. Volume 4 devoted Laplace transform. No, right now we are doing here in such level. Okay, let me tell several moments. Here you see formulas which shows that we can convert Mellin transform to Fourier and back, and how connected with Laplace transform. But everywhere you see kernels. Kernels everywhere is power function in sense mathematical system. I gave here such information. This is Parseval relation which can be used for evaluation integrals. We need to evaluate Mellin transform each function and then make this Parseval relation. And we are doing this in reality, but more effectively and extended this for product of arbitrary set of Fox functions. It was done together with my courses. Currently, I'm working with Elina Shishkina, professor from Voronezh, and with Timur Sadykov, who listened this lecture, I think. Here I especially show 2 formulas. People sometimes don't feel what is it going, but we are doing absolutely new level of mathematical calculus, because, you know, power from product, it is not power from each of function. We have coefficients. I found all these coefficients. The same for logarithm. If you link, you can come to this. Oh, what is it? I should remove. How to do it? Okay. The same you can link to this Wolfram function site and other, and you find a lot of important formulas. I still did not publish fully. It should be published somehow. Two wealth of mathematical functions, classical and computers. Because computers wealth, which realized in Maple, Mathematica, and other existing systems, are different, is different from classical, which you got from handbooks and from different sources. Now here I show. You can run this again. We have here A, B as parameters for Fox function. It is Fox transform. H function stays in kernel. And A and B is here. And here we have this relation which we saw. And then what I made, I generated arbitrary functions. I took function which people like, Mehta-Kleffler function. And we have Mehta-Kleffler equal to this Fox representation. You can take different kernels. And then I convert to then evaluated Fox transform for situation when we have Fox equal to Mehta-Kleffler, and then I run test. I show you this test, and I got corresponding results. No, this is Fox transform with Mehta-Kleffler kernel, and a result for variation of these functions. Again, about convergence condition, I keep silence in this talk, but I already have instrument and know how to do it, and I'm doing this in programs. I hope in this year people will see everything. Now here you find example. Then I took other transforms, Hankel transform. You saw today in my lecture up this Hankel transform. I made similar evaluations. Now here we with Parker should think about why about 30 examples were lost. Not lost, never done, maybe. I don't know. We should look. But in any case, we convert function to Fox form and then apply our generic formula for evaluation integrals from product of two Fox functions. In this area, you find a lot examples. Sometimes not everything is working. Last example here is evaluation Weyl integral. Again, I made evaluation. I looked how mathematical hand can do it. Sometimes I put timing. Mathematica evaluates this integral, gives result with conditions, and we also can evaluate. But here I just compare result which I produced, it's our, and Mathematica produced this one. Full simplify gives 1 for conditions. And again, not everything done. Lost 15 cases. I will look what it is. Okay. Now I present definitions of 67 transforms for which we can make similar evaluations but not made yet. Sometimes you see name Oleg. It's interesting moment. In reality, indeed, I developed this transform. Indeed, I found a situation that such kernel is particular case of Meyer-G function. I don't know, it's my formula. And kernel Mellin transform from this includes 3 gamma in numerator and 3 gamma in denominator. So it is more generic than transforms from Bushman. This is case of my transform. And similar love, you can find here name love. It's also case. And I met Love in Minsk. Professor Love came from Australia. And he came without winter clothes. Came like from summer, did not think that weather is different. At that time, I was in Minsk on conference. It was about almost 30 years ago. So we met. But with Bushman, I did not meet. He invited me, but I did not came by reasons that I started to work here. No, in any case, you see here a lot of integral transforms which is not realized yet. Altogether, it will be like about 100 maybe. But in this situation, I just collected all kernels, and again, one more test. I converted all these kernels to what I made. Again, percent I should remove, of course. At first, I converted to Meyer-G form. Then I used internal command, but I have already new code for doing such things. And for each transform, for example, this transform, kernel for transform Weyl, we have seen gamma divided on gamma, and this is constant, gamma beta constant. So here we have, in my classification, plus S, and here also plus S. And next transform, which I called my transform, we see minus s, minus s, minus s, divided minus, minus, minus again, and constant factor, gamma constant. I ignore it, of course. No, in any case, here you see kernels and their images through Mellin transforms from kernels. This is kernels of integral transform partially, which you saw upper or different a little. Some transforms has name. I gave such name like Hardy transform. I remember Teachmarsh because I met at first time in these books by name. You see, no transform with such kernel very famous Ries kernel of Ries integral transform. This one may be Hardy transform. So we have, I spent 40 minutes and I can stop or can continue to talk and I can listen questions. Maybe you have questions. It's up to you. Thank you very much.
Thank you very much for your presentation. Do we have any questions or comments?
No question.
Hello.
Huh? Elena.
Good afternoon. Yes. Good afternoon.
Good afternoon.
Here, the internet connection is very bad, unfortunately. So probably I
I
missed.
see you.
What was the connection to the fractional calculus? Which transform or transforms were connected to the fractional calculus, which we can use for solving fractional differential equations?
No, okay. I will answer on this question. Let's look on this one. Case. Ries transform. Let's look.
Ries transform.
Huh?
Excuse me, which transform? Ries?
No, I called this, maybe not very good transform. Okay, this popular transform with absolute value. Let's look on structure here. Gamma S, gamma minus S with a little movement. Gamma minus S, gamma plus S with a little add. If you take only this guy and this guy, you can find in my list here. Original, it will be Riemann Liouville, fractional integral. If you take this guy, and this guy, original, this guy, original, it will be Weyl, fractional integral. And here they multiply each on other. It is composition of these transforms. And the composition, Weyl and this Riemann Liouville gives transform with such kernel. But how many free parameters here? Only beta. If I put here S plus nu, and here I can put plus mu, I can introduce additional parameters. So we have 4 guys with 3 parameters. And in particular cases of this will be a Cauchy kernel. It means Hilbert transform. Or we can make this transform with this, this plus s and this minus s. If we take this pair, it will be Hankel transform only.
With
And
Bessel function.
this and this together, other pair gives again Hankel transform. So transform with such kernel we can produce from composition of 2 Hankel transforms. So you see how many situations. Okay. For example, you can take these 2 guys and this, and it is also transform. But what to do with this one? It is in denominator. And it is image of inverse Laplace transform. So composition of this and this, it is transformed like with kernel F11. It means kernel hypergeometric 1F1 produced as kernel. And this component in denominator, it is produced from Laplace inverse. So composing these 2 guys produce this one. You see how many variants. Maybe thousands and thousands articles published in these connections. A lot publications. But people who is doing very, very often does not see what I'm talking you right now about structure of integral transforms, and that this transform with Fox in kernel can be decomposed on many more simple transforms. Direct or inverse transforms connected with classical transforms. Open any book about integral transforms, you will find that majority transforms, classical transforms, has kernel which cases of this Fox function. Okay, next question.
Okay, thank you.
Mm-hmm.
Thank you. Do we have any other questions?
No, if no questions, I can add something. I have time. How long?
Yes.
Okay. I mentioned that in reality we are doing other computer world of mathematical functions. I show you 2 formulas, including floor. Why it is different world? Because major axiom, which like Euclidean, in Euclidean geometry, we have postulate that about parallel lines, you know this, maybe 5th axiom that through point out of line only one parallel line can be made. And here, the role of this axiom is the following statement. Absolutely for all evaluations, numerical evaluations, in all computer systems existing now, provided under condition that argument any complex numbers between minus pi and plus pi, including plus pi. Argument in this main plane for which we make numerical evaluations. And nobody, I think, before me, strange, but it is reality, seriously think about consequences for formulas if we have such statements, such statement. And Wolfram function site, which include formulas, no, a lot of formulas, they are connected with inverse functions, multi-valued functions. And I developed basic corrections and two formulas you saw today about these properties that, for example, logarithm product is not equal sum of logarithm. People sometimes knew and feel it, but did not know how to correct. I gave corrections for such formulas, verified on computer system everywhere, and it includes floor function, basically plus pi, minus pi, no such moment, or plus 0. And this situation is not described well, practically not described in literature. It will be very useful if people who knows not only Mathematica but Maple try to describe this effect. Of course, in future computers will handle many sheets situations for functions like logarithm and other many valued functions. Yes, but now we live in one plane. It's like in space we cannot trip to space with 4, 5, or 6 measure. We live in such our space. Okay, this is one moment which I want. Other moment, I have dream to realize some kind handbook, electronic handbook, and with collection and evaluation of existent doable integrals. And I am doing this job. I started with my colleagues and friends. We started attack when we have several forks under integral, product of 3 forks, 4 forks, and so on, arbitrary set of forks. And then, of course, we can go to other constructions a little, but it's interesting to see what happened. Right now, I show you these horrible sums, formulas, and in my situation, I started to think about this 50 years ago, more maybe. Returned to this idea many times, but development, multi-dimensional residues, which provided by Zich, Sadikov, and other authors in these areas who published books and articles allowed to move in this direction, allowed to evaluate examples and to start understanding what was happened. Basically, we have interesting situation. I know from which we can build result. In sense, residues. Now I know more how to build sums of residues. And we produced groups of double or triple. We can produce sums, residues, but I don't know which from these multisums should be included in output for integral and under which conditions, restrictions. This I still don't know. And we have rule, hidden rule from nature about this. Yeah. No, sorry, it's a message came. Yes. And we started to work. I will prepare more examples in this area to handle different situations. But now I know that we have 12 candidates from which I can build output with coefficients like 0, 1, or -1. Thank you. I see.
Thank you.
Arran.
I think there is a question from Lorenzo Cristofaro.
Yeah, thank you. I would like to thank Professor Marichev for this really nice talk and for the implementation of Fox-H functions in Wolfram Alpha. I think they are really useful. And I would like to ask a question related to this last topic he was talking about. If I didn't understand if you already have, or if there exists any example of Fox-H functions where the poles coincide such that the residue are, let's say, a bit troublesome. And if you have
You're
any...
talking logarithmic cases, yes?
or also, because if I will remember it, it happens when where you have, let's say, a pose where there is like a double coincidence, but in principle, the residue could have also more complicated form. Maybe I'm not sure, but yeah, for example, this one of good logarithm. If you have any example there in Wolfram, or if you in literature, or if you are planning to implement one of these more difficult functions on Wolfram Alpha.
Sorry, I prefer to read your message.
Yeah. I will
No.
write down.
Listen. I will answer, will try to answer. Now I answer as I understood. You
Sure.
mentioned that sometimes we have more difficult situation when poles can coincide, and I call this situation logarithmic cases, yes?
Okay, yes.
Okay. I will answer. Right now I know answer. I started to fight with this situation being in Minsk when I work with my first book, then my former PhD student, Viktor Adamchik, he came with me to Wolfram research in 1990, 35 years ago. Yes, Viktor Adamchik, by my order, include investigation logarithmic cases for Meyer-G function. Yes, order 4 we were made. Then I stopped. It's so horrible to do this. But here, this problem give got new life, because I found wonderful super function which you don't know maybe. It is Bell Y polynomials. Bell Y and Y, Y, yeah, polynomials. And I used this and made a program for evaluation Fox H in poles, pole. If this pole has coincide an arbitrary set of poles. It is n order pole. And program still did not implement it, but it exists. I meet here problem which can be solved not by me. Combinatoric problem. And problem is the following. For condition that this point is such horrible pole, we need to write system diaphantic equation. And somehow we should say something about its solution. Under condition that we have so ugly point where ne poles coincide, we need to write this system. Even for case of 2 measure, situation 2, it is system diaphantic equation. How to solve it? No, I can formulate, of course, problem is exists. Somebody else will solve after us. Yes, but in any case, it's doable, and I hope to publish this evaluation and make exercises.
Okay, thank you. Thank you very much then. Thank you.
Thank you very much. Are there any other questions, comments? All right, then we thank Professor Marichev again for his talk, and I will stop the recording here.